All right, time for part two. More fun with simple harmonic motion. Just a recap of what we did before. We drew a picture of a mass and spring system, and it would go around these four different uh, situations here. 0, A, 0, or the origin, minus A. And at first the mass was pulled out, so the spring was stretched. Then the mass goes back to its resting position, but now it's moving. Then the mass would overshoot and the spring would be compressed. And then the mass would be back at its equilibrium position, but it would be moving. And this is a cycle, so you go from one drawing to the other to the other. I suppose it could go either way. Um, well, no, the direction wouldn't work that way. Entropy. This is a cycle, and I wanted to make some notes about this. First note I wanted to make is that in this top drawing, we have a maximum displacement, but we have no velocity. It's stopped momentarily. This drawing, we have a displacement of 0. We're back at our equilibrium position, but we have a maximum velocity. In this drawing, we have a maximal displacement, although it's in the negative direction, and we're back to 0 velocity. And here, we have a 0 displacement, but our velocity is a maximum. Question is, what's going on with the acceleration in each of these situations? And that's a lot harder to see. I mean, we can observe motion and we can observe position quite readily. So to get at the acceleration, you can either treat this as a differentiation process and think about what the function might be. You know, we know it's a cosine or a sine kind of thing. Or we can say, look, the acceleration is coming from the force. So where the spring is stretched the most, we're going to have maximum acceleration. And where the spring is at its resting length, we're going to have 0 acceleration. Where the spring is compressed the most, we're going to have maximal acceleration. And where the spring is at its resting length, we're going to have 0 acceleration. That's the best way to think about this. Now, it is kind of counterintuitive because this is not moving here, but it is in the process of changing its motion the most. And then to touch ground again with what we've already said, this scene here represents having spring potential energy. This scene here represents having kinetic energy. This scene here represents having spring potential energy, and this has kinetic energy. Now, there's one thing we can do, and this ties into what we did before. We can use this energy conservation to figure out what the maximum velocity is. You see, the maximum amount of spring potential energy, when you pull it to the side the distance a, that is the maximum amount of energy. That is the energy of the system. And now when it's all going to be kinetic, we can figure out what velocity that represents. So the potential energy from this diagram is going to be equal in magnitude to the kinetic energy from that diagram. Potential energy in a spring is 1/2 kx squared, and kinetic energy is, of course, 1/2 mv squared. Cancel the m's, cancel the 1/2s, move the m to the other side, and then put in for x what it is. It's a. We know what x is at this point. And then when you do the math, Vmax equals A times the square root of K over M. And in fact, at any other time or any other position, the velocity is K over M times A squared minus X squared. Whatever spot in the middle between these two diagrams you stop, you can also figure out. But this is the one I wanted to get into your head here. We can figure out the maximum speed, all without any kind of differentiation or other kind of craziness that we did. Okay, I wanted to talk for a second. When we did the differential equation, we were able to solve for the position as a function of time, and we used cosine, although we could have used sine, and it had a parameter a, which tells you the amplitude of the motion. You can get that by just observing the motion. And it had a parameter omega, which told us something else, and I want to talk about that, but just recap here. This was minus a omega sine omega t, and a as a function of t was then minus a omega squared cosine omega t. And this is how we solved the differential equation. We plugged this in for the second derivative, this in for the other thing, and we discovered that omega must be the square root of k over m in order for this to be the solution. And what is this omega? So omega is an angular speed. That's the letter we use for angular speed. So what is this the angular speed of? Well, if we draw a circle, okay, not the best circle I've ever drawn, like the unit circle, although this is a circle of radius a. And we put a little imaginary particle on this circle and we have it go around the circle at the speed omega. This this thing will go around at a certain speed and take a certain amount of time to go around. So omega can tell us the time that this is going to take to do its physical thing. And this is a diagram of phase. Some people call it phase space, but it's just a diagram, an imaginary circle, and this point goes around this circle in exactly the same time as this system goes through its gyrations. Think about this for a second. What is the x projection of this thing? Well, it starts at a, moves to 0 in x, moves to minus a in x, then moves to 0 in x. It is actually this thing right here. It is a cosine omega t. The x projection of something going in a circle goes back and forth in a linear way, just like this system goes back and forth in a linear way. So this imaginary diagram has some relevance to this thing right here. Sometimes we call this the angular speed, and sometimes we call it the angular frequency. And so this phase diagram is fairly important. Let's, without clogging up this diagram anymore, let's do something new, okay? Let's talk about another system. Not a mass and spring system that goes boingy, boingy, boingy back and forth, but perhaps a new kind of mass and spring system. Let's talk about the torsional pendulum. Now the torsional pendulum, first you start with a very heavy mass, and I'm going to make my mass in as a disc, as a circle, and then you connect it, hang it from a thick rod. Now the rod is made of steel, and it's just flexible enough that you can bend it, and this disc has a moment of inertia I, and so if we were to displace this by a distance theta, twist it, then the rod would get twisted and it would twist back, and this thing would wiggle back and forth in a circular fashion, in a torsional fashion. Now, this kind of a spring, this twisting kind of spring, a torsional spring, has its own spring constant and its own Hooke's law, and that is that the return torque is minus some constant times how far you twisted it. This beta is the torsional constant, tells you how stiff or difficult to twist this rod is. If this was a string, it would be very easy to twist it, but if this was a solid rod, it might be more difficult. Beta is not the only letter that gets used. Sometimes in your book they use a kappa, which is a Greek capital K. Anyway, this is the restoring force, so we can put this in to Newton's second law, but this is Newton's second law written for torques. Torque net equals I times alpha. Put this force in and we have minus beta theta equals I times alpha. I love this because it's got all kinds of Greek letters. Move the I to the other side and we have minus beta over I times theta equals, and now alpha is the second derivative of theta with respect to time. Just like A is the second derivative of x with respect to time, this whole thing is just like what we did with the mass and spring system, only it involves things going in circles and it has different constants. So we're going to guess that theta is going to be A times sine of omega t. I'm using sine this time because I don't want to show any favoritism to cosine, but again, it all depends on how you start the system. If you start the system by twisting and then letting go, you probably should use a cosine because cosine as a function starts with a number. But if you start it by giving it a push, like a rub, or you hit it with your thumb, then you should probably use sine because sine starts at 0. Okay, that means that omega, and okay, now this is going to be a problem. This is going to be, no, I'm going to say d theta dt, because we got an omega here. Unfortunately, we use the same letter. The a omega cosine omega t, and then d squared theta dt squared is going to be minus a omega squared sine omega t. Oh boy, I didn't leave a lot of room. All right, so this goes back in here, and we have that minus beta I times A sine omega t equals minus A omega squared sine omega t, and this is the correct solution so long as omega is the square root of beta over I. So we have a very similar situation. We have an angular frequency, and then of course the period of the system is always 2 pi over the omega for the system, so that would be 2 pi times the square root of I over beta. So I just went through another thing where we generated the differential equation by taking the restoring force, which is linear in theta, plugging it in to Newton's second law, writing the acceleration as a second derivative of the function, guessing what the solution looks like, and then finding out what has to be true to ensure that that is the solution. Now, one more thing I want to point out here, and that is that our omega for the original mass and spring system was square root of k over m. And then for the torsional pendulum, omega was beta over I. In general, omega for any system is something springy over something massy. Springy is a real word, massy isn't, but I'm trying to go with a common thread. In other words, something that characterizes the restoring force and the energy in the system divided by something that characterizes the inertia of the system. In the case of a mass spring system, the spring constant tells you how springy it is, and the mass tells you how much inertia there is. In the case of a torsional pendulum, this coefficient beta tells you how springy things are, and I, the rotational inertia, the rotational moment of inertia, tells you how much it resists motion. So this is kind of a cool little guiding principle for this thing. Okay, that's enough. That's another application. We're going to do some more like this in little bits and fits.